Color. Describe what happens when sunlight is passed through a triangular shaped prism. Describe how the reflection of light affects an object's color. Describe what determines whether a material reflects, transmits, or absorbs light of a particular color. Describe white light. State the three colors that can be combined to form almost any color. Define complementary colors. Describe color mixing by subtraction. Explain why the sky is blue, why sunsets are red, and why water is greenish blue. Explain how atoms emit light. The big idea. The color of objects depend on the color of the light that illuminates them. Roses are red and violets are blue. Colors intrigue artists and physics types too. To the physicist, the colors of things are not in the substances of the things themselves. Color is in the eye of the beholder and is provoked by the frequencies of light emitted or reflected by things. We see red in a rose when light of certain frequencies reaches our eyes. Other frequencies will provoke the sensations of other colors. Whether or not these frequencies of light are actually perceived as colors depend on the eye-brain system. Many organisms, including people with defective color vision, see no red in a rose. Discover, how can color be used to identify elements? View an incandescent bulb through a diffraction grating and record what you see using crayons or colored pencils. View a fluorescent lamp through a diffracting grating. Record your observations. View a light source of your choice using the diffraction grating and record your observations. Caution: never view the sun through the diffraction grating. Looking directly at the sun can damage your eyes. Analyze and conclude. 1. Observing. In what ways were the colors you viewed the same? In what ways were the spectra different? Predicting. Do two incandescent bulbs of different brightness have the same colors? Making generalizations. How may color be used to identify elements found both here on Earth and in space? 28.1. The color spectrum. Isaac Newton, shown in figure 28.1, was the first to make a systematic study of color. By passing a narrow beam of sunlight through a triangular-shaped glass prism, Newton showed that sunlight is composed of a mixture of all the colors of the rainbow. The prism cast the sunlight into an elongated patch of colors on a sheet of white paper. Figure 28.1, Newton passed sunlight through a glass prism to form the color spectrum. Newton called the spread of colors a spectrum and noted that the colors were formed in the order red, orange, yellow, green, blue, and violet as shown in figure 28.2. Sunlight is an example of what is called white light. White light is a combination of all colors. Under white light, white objects appear white and colored objects appear in their individual colors. Newton showed that the colors in the spectrum were probably not of the prism but of the white light itself. He demonstrated this when he recombined the colors with a second prism to produce white light again. In other words, all the colors, one atop the other, combine to produce white light. Strictly speaking, white is not a color, but a combination of all colors. 28.2, when sunlight passes through a prism, it separates into a spectrum of all colors of the rainbow. Black is similarly not a color itself, but is the absence of light. Objects appear black when they absorb light of all visible frequencies. Carbon soot is an excellent absorber of light and looks very black. The dull finish of black velvet is an excellent absorber also. But even a polished surface may look black under some conditions. For example, highly polished razor blades are not black, but when stacked together and viewed end on, as in figure 28.3, they appear quite black. Figure 28.3, when a stack of razor blades bolted together is viewed end on, the edges appear black. Light that enters the wedge-shaped spaces between the blades is reflected so many times that most of it is absorbed. Chameleons linked to zoology. The chameleon can change its colors to blend into the background or to suit its mood. Its skin consists of stacks of cells with red, yellow, and blue pigments, as well as brown melanin. The chameleon expands cells of one color while shrinking those of another to create different skin hues. A chameleon's color depends on whether it is lounging, flirting, or fighting. When the chameleon is angry, melanin levels go up, masking the other colors, and the skin looks dark. Think, when red light shines on a red rose, why do the leaves become warmer than the petals? The leaves absorb rather than reflect red light, so the leaves become warmer. When green light shines on a red rose, why do the petals look black? The petals absorb rather than reflect green light, so the rose appears to have no color at all, black. Most of the light that gets between the closely spaced edges of the blades gets trapped and is absorbed after being reflected many times. Black objects that you can see do not absorb all light that falls on them, for there is always some reflection at the surface. If not, you wouldn't be able to see them. Concept check. How did Isaac Newton show the sunlight is composed of a mixture of all colors of the rainbow? 28.2. Color by reflection. The colors of most objects around you are due to the way the objects reflect light. The color of an opaque object is the color of the light it reflects. Light is reflected from objects in a manner similar to the way sound is reflected from a tuning fork when another that is nearby sets it into vibration. A tuning fork can be made to vibrate even when the frequencies are not matched, although at significantly reduced amplitudes. The same is true of atoms and molecules. We can think of atoms and molecules as three-dimensional tuning forks with electrons that behave as tiny oscillators that whirl in orbits around the nucleus. Electrons can be forced temporarily into large orbits by the vibrations of electromagnetic waves such as light. Like acoustical tuning forks, once excited to more vigorous motion, electrons send out their own energy waves in all directions. Differences among materials. Different materials have different natural frequencies for absorbing and emitting radiation. In one material, electrons oscillate readily at certain frequencies. In another material, they oscillate readily at different frequencies. At the resonant frequencies where the amplitudes of oscillation are large, light is absorbed. Recall from the previous chapter that glass absorbs ultraviolet light for this reason. But at frequencies below and above the resonant frequencies, light is re-emitted. If the material is transparent, the re-emitted light passes through it. If the material is opaque, the light passes back into the medium from which it came. This is reflection. Most materials absorb light of some frequencies and reflect the rest. If a material absorbs light of most visible frequencies and reflects red, for example, the material appears red. If it reflects light of all the visible frequencies as shown in figure 28.4a, it will be the same color as the light that shines on it. If a material absorbs all the light that shines on it, as shown in figure 28.4b, it reflects none and is black. Figure 28.4a. This square reflects all the colors illuminating it. In sunlight, it is white. When illuminated with blue light, it's blue. B. This square absorbs all the colors illuminating it. In sunlight, it is warmer than the white square. When white light falls on a flower, light of some frequencies is absorbed by the cells in the flower and some light is reflected. Cells that contain chlorophyll absorb light of most frequencies incident upon them and reflect the green part, so they appear green. The petals of a red rose, on the other hand, reflect primarily red light with a lesser amount of blue. Interestingly enough, the petals of most yellow flowers, such as daffodils, reflect red and green as well as yellow. Yellow daffodils reflect light of a broader band of frequencies. The reflected colors of most objects are not pure single frequency colors, but are composed of a spread of frequencies. So something yellow, for example, may simply be a mixture of colors without blue and violet, or it can be built of red and green together, light sources. An object can reflect only light of frequencies present in the illuminating light. The color of an object therefore depends on the kind of light used. A candle flame emits light that is deficient in the higher frequencies. It emits a yellowish light. Things look yellowish in candlelight. An incandescent lamp emits light of all the visible frequencies, but is richer towards the lower frequencies, enhancing the reds. A fluorescent lamp is richer in the higher frequencies, so blues are enhanced when illuminated with fluorescent lamps. In a fabric with a little bit of red, for example, the red will be more apparent when illuminated with an incandescent lamp than with a fluorescent lamp. Colors in daylight appear different from the way they appear when illuminated with either of these lamps, as shown in figure 28.5. The perceived color of an object is subjective, although color differences between two objects are most easily detected in bright sunlight. Concept check. What determines the color of an opaque object? 28.5. Color depends on the light source. 28.3. Color by transmission. The color of a transparent object is the color of the light it transmits. A red piece of glass appears red because it absorbs all the colors that compose white light except red, which it transmits. The blue piece of glass in figure 28.6 appears blue because it transmits primarily blue and absorbs the other colors that illuminate it. The material in the glass that selectively absorbs colored light is known as a pigment. From an atomic point of view, electrons in the pigment atoms selectively absorb light of certain frequencies in the illuminating light. Light of other frequencies is re-emitted from atom to atom in the glass. Figure 28.6. Blue glass transmits only energy of the frequency of blue light energy, and the other frequencies is absorbed and warms the glass. The energy of the absorbed light increases the kinetic energy of the atoms, and the glass is warmed. Ordinary window glass is colorless because it transmits lights of all visible frequencies equally well. Check. What determines the color of a transparent object? 28.4. Sunlight. White light from the sun is a composite of all the frequencies, all the visible frequencies. The brightness of solar frequencies is uneven, as indicated in the graph of brightness versus frequency in figure 28.7. The graph indicates that the lowest frequencies of sunlight in the red region are not as bright as those in the middle range yellow and green region. Yellow-green light is the brightest part of sunlight. Since humans evolved in the presence of sunlight, it is not surprising that we are most sensitive to yellow-green. Figure 28.7. The radiation curve of sunlight is a graph of brightness versus frequency. Sunlight is brightest in the yellow-green region in the middle of the visible range. That is why it is more and more common for new fire engines to be painted yellow-green, particularly at airports where visibility is vital. This also explains why at night we are able to see better under the illumination of yellow sodium vapor lamps than we are under tungsten lamps of the same brightness. The blue portion of sunlight is not as bright, and the violet portion is even less bright. The graphical distribution of brightness versus frequency in figure 28.7 is called the radiation curve of sunlight. Most whites produced from reflected sunlight have this frequency distribution. Concept check. Which visible frequencies make up the brightest part of sunlight? What is the color of a candle's reflection? 1. Hold a candle flame, match flame, or any small source of white light in between you and a piece of colored glass. How many reflections do you see? What is the color of the flame reflected from the front surface, from the back surface? Think. Explain why the flame's reflections are the colors that they are. Artist, physics on the job. Artists use both creativity and science to paint. By mixing pigments in just the right proportions, an artist can produce all the colors necessary to capture an image. To artists, mixing colors can be a matter of trial and error. They add colors until they achieve the desired color. As they do so, they are using the process of color mixing by subtraction. Some artists work independently, selling their works to interested buyers. Others are employed to create images for books, movies, or advertisements. 28.5. Mixing colored light. Light of all visible frequencies mixed together produces white. Interestingly enough, white also results from the combination of only red, green, and blue light. When a combination of only red, green, and blue light of equal brightness is overlapping on a screen, as shown in figure 28.8, it appears white. When red and green light alone overlap, the screen appears yellow. Red and blue light alone produce bluish red color called magenta. Green and blue light alone produce a greenish blue color called cyan. Figure 28.8. When red light, green light, and blue light of equal brightness are projected on a white screen, the overlapping areas appear different colors. Where all three overlap, white is produced. This can be understood if the frequencies of white light are divided into three regions as shown in figure 28.9. The lower frequency red end, the middle frequency green part, and the higher frequency blue end. The low and middle frequencies combined appear yellow to the human eye. The middle and high frequencies combined appear greenish blue, cyan. The low and high frequencies combined appear bluish red, magenta. You can make almost any color at all by overlapping red, green, and blue light and adjusting the brightness of each color of light. This amazing phenomena is due to the way the human eye works. What color does red light plus blue light make? Magenta. Figure 28.9, the low frequency, middle frequency, and high frequency parts of white light appear red, green, and blue. To the human eye, red and green equal yellow, red and blue equal magenta, and green and blue equal cyan. The three colors do not have to be red, green, and blue, although those three produce the highest number of different colors. For this reason, red, green, and blue are called the additive primary colors. Color television is based on the ability of the human eye to see combinations of three colors as a variety of different colors. Notes: all the colors added together produce white. The absence of all color is black. A close examination of the picture on most color television tubes will reveal that the picture is made up of an assemblage of tiny spots, each less than a millimeter across. When the screen is lit, some of the spots are red, some green, and some blue. At a distance, the mixture of these colors provide a complete range of colors, plus white. Concept check. Which three visible frequencies combine to form almost any color? 28.6, complementary colors. What happens when two of the three additive primary colors are combined? Red and green make yellow. Red and blue equal magenta. Blue and green make cyan. Discover. What do you see when your color receptors are fatigued? 1. What are the complementary colors of the flag? 2. Stare at the flag for a minute or so. 3. Then look at a piece of white paper. What are the colors of the after image? Think. When you stare at a colored object for a while, the color receptors in your eyeballs become fatigued. The fatigued receptors send a weaker signal to the brain. Use this idea to explain the colors of the after image. What color does white light minus yellow light appear? Blue. What color does white light minus green light appear? Magenta. Now, a little thought and inspection of figure 28.8 will show that when we add in the third color, we get white. Yellow plus blue equals white. Magenta plus green equals white. Cyan plus red equals white. When two colors are added together to produce white, they are called complementary colors. For example, we see that yellow and blue are complementary because yellow, after all, is a combination of red and green. And red, green, and blue light together appear white. 28.8. When red light, green light, and blue light of equal brightness are projected on a white screen, the overlapping areas appear different colors. Where all three overlap, white is produced. By similar reasoning, we see that magenta and green are complementary colors, as are cyan and red. Every color has some complementary color that, when added to it, will produce white. Figure 28.10 shows how 6 blocks and their shadows appear different colors under light of different colors. Now, if you begin with white light and subtract some colors from it, the resulting color will appear as the complement of the one subtracted. Not all the light incident upon an object is reflected. Some is absorbed. The part that is absorbed is in effect subtracted from the incident light, as shown in figure 2811. Figure 2811. When white light passes through all three transparencies, light of all frequencies is blocked, subtracted, and we have black. Where only yellow and cyan overlap, light of all frequencies except green is subtracted. Figure 2810. 6 blocks and their shadows appear as different colors depending on the color of light that illuminates them. A. The blocks are lit by white light. B. The blocks are lit by blue light. C. The blocks are lit by red light from the right and green light from the left. D. The blocks are lit by blue light from the left and red light from the right. For example, if white light falls on a pigment that absorbs red light, the light reflected appears cyan. A pigment that absorbs blue light will appear yellow. Similarly, a pigment that absorbs yellow light will appear blue. Whenever you subtract a color from white light, you end up with the complementary color. Concept check. What happens when you combine any color of its complementary color? 28.7. Mixing colored pigments. Artists know that if we mix red, green, and blue paint, the result will not be white, but a muddy dark brown. Red and green paint certainly do not combine to form yellow, as red and green light do. The mixing of paints and dyes is an entirely different process from the mixing of colored light. Paints and dyes contain finely divided, solid particles of pigments that produce their colors by absorbing light of a certain frequency and reflecting light of other frequencies. Pigments absorb light of a relatively wide range of frequencies and reflect a wide range as well. In this sense, pigments reflect a mixture of color. When paints or dyes are mixed, the mixture absorbs all the frequencies each paint or dye in it absorbs. Blue paint, for example, reflects mostly blue light, but also violet and green. It absorbs red, orange, and yellow light. Yellow paint reflects mostly yellow light, but also red, orange, and green. It absorbs blue and violet light. When blue and yellow paints are mixed, then between them they absorb all the colors except green. As figure 2812 shows, the only color both yellow and blue pigments reflect is green, which is why the mixture looks green. Figure 2812. When blue and yellow pigments are mixed, they produce a green mixture. A. Blue pigments reflect green, blue, and violet lights. B. Yellow pigment reflects red, orange, yellow, and green light. C. When blue and yellow pigments are mixed, the only common color reflected is green. Table 28.1 summarizes the various color subtractions. This process is called mixing by subtraction. To distinguish it from the effect of mixing colored light, which is called color mixing by addition. So when you cast light on the stage at a school play, you use rules of color addition to produce various colors. But when you mix paint, you use the rules of color subtraction. You may have learned as a child that you can make any color with paints of three so-called primary colors, red, yellow, and blue. Actually, the three paints or dye colors that are most useful in color mixing by subtraction are magenta, bluish red, yellow, and cyan, greenish blue. Magenta, yellow, and cyan are the subtractive primary colors used in printing illustrations in full color. 2813, Sneasley's rich colors represent many frequencies of light. The photo, however, is a mixture of only yellow, magenta, cyan, and black. Color printing is done on a press that prints each page with four differently colored inks: magenta, yellow, cyan, and black, in succession. Each color of ink comes from a different plate, which transfers the ink to the paper. The ink deposits are regulated on different parts of the plate by tiny dots. Examine the colored pictures in this book or in any magazine with a magnifying glass and see how the overlapping dots of three colors plus black give the appearance of many colors. Figure 2814 shows how to reproduce a photograph. Concept check. Which visible frequencies are absorbed by a mixture of paints or dyes? Figure 2814, only four colors of ink are used to print color illustrations and photographs: magenta, yellow, cyan, and black. The addition of the black produces the finished results. 28.8. Why the sky is blue. If a sound beam of a particular frequency is directed to a tuning fork of similar frequency, the tuning fork will be set into vibration and effectively redirect the beam in multiple directions. The tuning fork scatters the sound. Scattering is a process in which sound or light is absorbed and re-emitted in all directions. Figure 2815 illustrates how an atom can scatter a beam of light. In the atmosphere, light is scattered by molecules and larger specks of matter that are far apart from one another. 2815, a beam of light falls on an atom and causes the electrons in the atom to move temporarily in large orbits. The more vigorously oscillating electrons re-emit light in various directions. Light is scattered. The sky. We know that atoms and molecules behave like tiny optical tuning forks and re-emit light waves that shine on them. Very tiny particles do the same. The tinier the particle, the higher the frequency of light it will scatter. This is similar to small bells ringing at higher notes than larger bells. The nitrogen and oxygen molecules and the tiny particles that make up the atmosphere are like tiny bells that ring with high frequencies when energized by sunlight. Like the sound from bells, the re-emitted light is sent in all directions. It is scattered. Most of the ultraviolet light from the sun is absorbed by a protective layer of ozone gas in the upper atmosphere. The remaining ultraviolet sunlight passing through the atmosphere is scattered by atmospheric particles and molecules. The sky is blue because its component particles scatter high-frequency light. Of the visible frequencies, violet light is scattered the most, followed by blue, green, yellow, orange, and red, in that order. Red light is scattered only a tenth as much as violet. Although violet light is scattered more than blue, our eyes are not very sensitive to violet light. Our eyes are more sensitive to blue. So we see a blue sky as shown in figure 2816. 2816, the sky is blue because its tiny particles scatter high-frequency light. The blue sky between the viewer and the distant mountains produces bluish mountains. The blue of the sky varies in different parts under different conditions. Where there are a lot of particles of dust and other particles larger than oxygen and nitrogen molecules, the lower frequencies of light are scattered more. This makes the sky less blue, and it takes on a whitish appearance. After a heavy rainstorm, when the particles have been washed away, the sky becomes a deeper blue. The higher that one goes into the atmosphere, the fewer molecules there are in the air to scatter light. The sky appears darker when there are no molecules, as on the moon, for example. The sky is black. The clouds. Water droplets in a variety of sizes, some of them microscopic, make up clouds. The different size droplets result in a variety of frequencies for scattered light. Low frequencies from larger droplets and higher frequencies from tiny droplets of water molecules. Notes: there are no blue pigments in the feathers of a blue jay. Instead, there are tiny alveolar cells in the barbs of its feathers that scatter light, mainly high frequency light. So a blue jay is blue for the same reason the sky is blue, scattering. The overall result is a white cloud, as shown in figure 2817. The electrons in a tiny droplet vibrate together and in step, which results in the scattering of a greater amount of energy than when the same number of electrons vibrate separately. Hence, clouds are bright. Larger assortment of droplets absorb much of the light incident upon them, and so the intensity of the scattered light is less. This contributes to the darkness of clouds composed of larger droplets. Further increase in the size of the droplets causes them to fall as raindrops, and we have rain. Concept check. Why is the sky blue? Figure 2817, the droplets that compose a cloud come in a wide variety of sizes, hence a wide variety of colors are scattered, which is why the cloud is white. Why are sunsets red? 28.9. The lower frequencies of light are scattered the least by nitrogen and oxygen molecules. Therefore, red, orange, and yellow light are transmitted through the atmosphere more readily than violet and blue. Red light, which is scattered the least, passes through more atmosphere without interacting with matter than light or any other color. Therefore, when light passes through a thick atmosphere, light of the lower frequencies is transmitted while light of the higher frequencies is scattered. At dawn and at sunset, sunlight reaches us through a longer path through the atmosphere than at noon. If molecules in the sky scattered low frequency light more than high frequency light, how would the colors of the sky and sunsets appear? If low frequencies were scattered more, red light would be scattered out of the sunlight on its long path through the atmosphere at sunset, and the sunlight to reach your eyes would be predominantly blue and violet. Distant dark mountains are bluish in color. What is the source of this blueness? Hint. What is between you and the mountains you see? If you look at distant dark mountains, very little light from them reaches you, and the blueness of the atmosphere between you and the mountains predominates. The blueness is of the low altitude sky between you and the mountains. Think. Distant snow-covered mountains reflect a lot of light and are bright, but they sometimes look yellowish depending on how far away they are. Why are they yellow? Hint. What happens to the reflected white light as it travels from the mountain to you? Distant snow-covered mountains often appear pale yellow because the blue in the white light from the heavy mountains is scattered on its way to you. The complementary color left is yellow. At noon, sunlight travels through the least amount of the atmosphere to reach Earth's surface, as shown in figure 2818. Then, a relatively small amount of light is scattered from sunlight. As the day progresses and the sun is lower in the sky, the path through the atmosphere is longer, and more blue is scattered from the sunlight. Less and less blue remain in the sunlight that reaches Earth. The sun appears progressively redder, going from yellow to orange. Notes: isn't it true that knowing why the sky is blue and why sunsets are red adds to their beauty? Knowledge doesn't subtract. Figure 2818. By the time a beam of light gets to the ground at sunset, only the lower frequencies survive, producing a red sunset. By the time a beam of light gets to the ground at sunset, all of the high frequency light has already been scattered. Only the lower frequencies remain, resulting in a red sunset. The sequence is reversed between dawn and noon. The colors of the sun and sky are consistent with our rules for color mixing. When blue is subtracted from white light, the complementary color that is left is yellow. The subtraction of violets leave orange. When green is subtracted, magenta is left. The relative amounts of scattering depend on atmospheric conditions, which change from day to day and give us a variety of sunsets. The next time you find yourself admiring a crisp blue sky, or delighting in the shades of bright clouds, or watching a beautiful sunset, just as the one shown in figure 2819, think about all the ultra tiny optical tuning forks vibrating. You'll appreciate these everyday wonders of nature even more. Notes: atmospheric soot warms Earth's atmosphere by absorbing light, while cooling local regions by blocking sunlight from reaching the ground. The effects of soot particles in the air range from triggering severe rains in one region to causing droughts and dust storms in another. Figure 2819. The sunset sky is red because of the absence of high frequency light. Why do you see the scattered blue when the background is dark, but not when the background is bright? Because the scattered blue is faint. A faint color will show itself against a dark background, but not against a bright background. For example, when you look from Earth's surface at the atmosphere against the darkness of space, the atmosphere is sky blue. But astronomers above who look below through the same atmosphere to the bright surface of the Earth do not see the same blueness. Concept check. Why are sunsets red? 2810. Why water is greenish blue? We often see a beautiful deep blue when we look at the surface of a lake or the ocean, as shown in figure 2820. But that is not the color of water. It is the reflected color of the sky. The color of water itself, as you can see by looking at a piece of white material underwater, is a pale greenish blue. Water is transparent to nearly all of the visible frequencies of light. Water molecules absorb infrared waves because they resonate to the frequencies of infrared. The energy of the infrared waves is transformed into kinetic energy and the water molecules. Infrared is a strong component of the sunlight that warms water. Water molecules resonate somewhat to the visible red frequencies. Figure 2820, ocean water is cyan because it absorbs red. The froth in the waves is white because its droplets of many sizes scatter many colors. This causes a gradual absorption of red light by water. A 15-meter layer of water reduces red light to a quarter of its initial brightness. There is very little red light in the sunlight that penetrates below 30 meters of water. When red is taken away from white light, what color remains? This question can be asked in another way. What is the complementary color of red? The complementary color of red is cyan, a greenish blue color. In seawater, the color of everything at these depths look greenish blue. It is interesting to note that many crabs and other sea animals that appear black in deep water are found to be red when they are raised to the surface. At great depths, black and red look the same. So, both black and red sea animals are hardly seen by predators and prey in deep water. They have survived an evolutionary history while more visible varieties have not. In summary, the sky is blue because blue from sunlight is re-emitted in all directions by molecules in the atmosphere. Water is greenish blue because water molecules absorb red. The colors of things depend on what colors are reflected by molecules, and also by what colors are absorbed by molecules. Concept check. Why is water greenish blue? 2811, the atomic color code, atomic spectra. When made to emit light, every element has its own characteristic color. The color is a blend of various frequencies of light. Light of each frequency is emitted when the electrons in an atom change energy states. These energy states are related to the orbits of electrons in the atom. Electrons surrounding the atomic nucleus have well-defined orbits. Another way of saying this is they have well-defined energy levels. Lower energy near the atomic nucleus and higher energy farther from the nucleus. When an atom absorbs external energy, one or more of its electrons is boosted to a higher energy level. We say such an energized atom is in the excited state. An excited state is a state with greater energy than the atom's lowest energy state. The excited stage is only momentary, for the electron is quickly drawn back to its original or lower level. When the electron transition occurs, the atom emits a throbbing pulse of light, a photon. Figure 2821 and 2822 model this process. After an excited atom emits light, it returns to its normal state. Notes. Most elements found on Earth and even organic molecules, complex and simple, are found in spectra of interstellar gases. Figure 2821. Light is emitted by excited atoms. 2822. A. The different electron orbits in an atom are like steps in energy levels. B. When an electron is raised to a higher level, the atom is excited. C. When the atom returns to its original level, it releases energy in the form of light. Relating frequency and energy. The frequency of the emitted photon, or its color, is directly proportional to the energy transition of the electron. In shorthand notation, frequency is proportional to energy. A photon carries an amount of energy that corresponds to its frequency. Red light from neon gas, for example, carries a certain amount of energy. A photon of twice the frequency has twice as much energy and is found in the ultraviolet portion of the spectra. when many atoms in a material are excited. Many photons with many different frequencies are emitted, all corresponding to transitions of electrons between many different levels. So measuring the frequencies of light in a spectrum is also measuring the relative energy levels in the atom emitting that light. Hence, the frequencies or colors of emitted light by elements are the fingerprints of the elements. Analyzing light. The light from glowing elements can be analyzed with an instrument called a spectroscope. This chapter began with a brief account of Newton's investigation of light passing through a prism. The spectrum formed in Newton's first experiment was blurry because it was formed by overlapping circular images of the circular hole in his window shutter. He later produced a better spectrum by first passing light through a thin slit and then focusing it with lenses through the prism and onto a white screen, as shown in figure 2823. Figure 2823, a fairly pure spectrum, is produced by passing white light through a thin slit, two lenses, and a prism. If the slit is made narrow, overlapping is reduced and the colors in the resulting spectrum are much clearer. This arrangement of thin slit lenses and a prism, or a diffraction grating, is the basis for the spectroscope. A simple spectroscope with a diffraction grating is shown in figure 2824. A spectroscope displays the spectra of light from hot gases and other light sources. Spectra is the plural of spectrum. The spectra of light sources are viewed through a magnifying eyepiece. It is found that the colors are the composite of a variety of different frequencies of light. Figure 2824. A spectroscope separates light into its constituent frequencies. Light illuminates the thin slit at the left, and then it is focused by lenses onto either a diffraction grating shown or a prism on the rotating table in the middle. The spectrum of an element appears not as a continuous band of color, but as a series of lines, as shown in figure 2825. Such a spectrum is known as a line spectrum. A line spectrum is a pattern of distinct lines of color, with each line corresponding to a frequency of light. The spectral lines seen in the spectroscope are lines of the slit through which the light passes. Note that each color line appears in the same position as that color in the continuous spectrum. A clear spectrum is produced when atoms are made to glow in the gaseous phase. In the solid phase, as in a lamp filament, where atoms are crowded together, the characteristic colors of the atoms are smudged to produce a continuous spectrum. 2825a. An incandescent bulb has a continuous spectrum. Each of the three elements, B, hydrogen, C, sodium, and D, mercury, has a different line spectrum. Much of the information that physicists have about atomic structure is from the study of atomic spectra. The atomic composition of common materials, the sun and distant galaxies, is revealed in the spectra of these sources. Even the element helium, the second most common element in the universe, was discovered through its fingerprint in sunlight. The spectrometer is a very useful and powerful tool. Concept check. What happens to an excited atom after it emits light? Summary. Sunlight is composed of a mixture of all colors of the rainbow. The color of an opaque object is the color of light it reflects. The color of a transparent object is the color of the light it transmits. Yellow-green light is the brightest part of sunlight. You can make almost any color at all by overlapping red, green, and blue light and adjusting the brightness of each. Every color has a complementary color that, when added to it, will produce white. When paints or dyes are mixed, the mixture absorbs all frequencies each paint or dye in it absorbs. The sky is blue because its component particles scatter high-frequency light. A beam of light at sunset contains only the lower frequencies, resulting in a red sunset. Water is greenish-blue because water molecules absorb red. After an excited atom emits light, it returns to its normal state.